Hello and welcome to another STEM in a Box video demonstration. My name is Dan Fleesick. In this video we'll be talking about density. What is it, how do you measure it, and why is it useful? Well, first of all, an object's density is simply its mass divided by its volume. You can think of it as the compactness of the object, basically how much stuff is crammed into it. So for example, if you have a block of lead and a block of wood that are the same size and shape, which one do you think would be heavier? Probably the lead, right? Because the lead is a very dense material. It's very well known as being heavy. But the question we want to answer here is, how do you actually measure density? And that's what I'll show you in this video. So let's go ahead and get started. Since this activity is part of the atoms and elements topic, I'm going to be using these small cubes of pure elements to demonstrate the technique of measuring density. So here I've got 6 cubes made of different metals, which come in this little bag, which comes in this little box. And they all look pretty similar to each other. They're all just various shades of gray, except for this one, of course, which is kind of a reddish color. And none of them are labeled at all, so how would we know which one is which? Well, measuring density is one good way to do it. I can already tell that they're pretty different just by holding them. So this one, for example, feels really, really light. It almost feels hollow, it's so light. And then this one is really, really heavy. That's very, very different. And then the other ones are they're all very different. They all feel a little bit different. But of course, just holding them, you're just looking at weight. And so what we really need here is density. So here is the data table that we're going to use for this activity. It comes with some instructions up top. We've got our table to actually record all information. And I've also added a table of the accepted densities of each of the possible elements that these cubes are. So that once we calculate the density of each of our cubes, we should be able to match those numbers up to these numbers in this table and figure out which cube is which metal. Since right now I'm not really sure which cube is which metal, I'm just going to set them on our data table on the numbers like this, so I remember which cube I've already tested and which I haven't. To calculate density, we're going to need 2 things: the cube's mass and its volume. Then all you do is divide the 2, and that's the density. Since mass and volume both have about 1 million different units that people use, density also has 1 million different units. So to keep things simple, we're just going to stick with metric and we'll use grams and cubic centimeters. First, we'll measure the mass. This is nice and easy to do with one of these scales. So first you remove the cover, turn it on, wait until it reads 0, and then make sure it's in grams. So see the little G there? If it's not in grams, you'll hit this middle button, the mode, to change it. It'll cycle through all the different things that it can measure until we're back at the G. Now all we got to do is put each cube on scale and record the mass. So we'll start with cube 1. And we get 7.8 grams. So I will record that on the data table. And then we'll just continue to do that for all 6 of our cubes. We get 8.8 for that one. Wow, 18.7. That one's heavy. .1. And 2.7. That one's very light. Okay, and there we go. Remember, when you're done with the scale, to always turn it off and put the cover back on. Next, we'll need the volume. Luckily, these elements are in nice regular shapes, so we can just calculate it directly without doing any fancy tricks. The best way to do this would be to use calipers if you have them, but I don't have a set, so we're going to try to use this ruler instead. And we'll see if that affects our accuracy at the end. Anyway, since this is a cube, all we need to do is measure each side to get the length, the width, and the height. So I'll start with cube 1, and remember we want to use centimeters here, so we'll do the centimeters side of the ruler. And I'll line that up at the 0. And it looks like just a hair under 1 centimeter. So I'll say 0.95, and we'll call that the length side. So the width, we'll just turn it to this side. That also looks like 0.95 to me. And in the height, we need to flip it so that we're measuring the third side. That looks like 0.9 to me. Now, you know, these are supposed to be cubes, so theoretically you should only have to measure one side and then use that for all three values. But we don't want to make assumptions like that when we're doing science, and so it's best to always measure everything. And you can see that that's kind of true here. So there's slight differences between the height and the other two measurements here, and we wouldn't have known that had we just assumed that all sides were equal. So once we have all three values, all we have to do is multiply those together. So I've got 0.95 times 0.95 times 0.90 gives me 0.81 as my volume. And that's cubic centimeters. You see, we multiplied centimeters together 3 times, so we get centimeters cubed. And that's the same process I'm going to follow for all the rest of our cubes. Okay, so that's done for all the cubes. Some of them were a little bit nicer than others. You see that some of these were exactly equal to 1, which was pretty nice. Some of them were off by a little bit. So again, that's why you don't want to assume anything in science. But now that we have our mass and our volume, all you need to do is divide the mass, the first column, by the volume, which is this column, and we'll get our density. So for the first cube here, we've got 7.8, and I'll divide that by 0.81, and we get 9.63. Second cube, 8.8 divided by 0.81. We've got 10.86 and 2.7. Okay, now that we've got our calculated densities, let's take a look at our table of accepted densities up top here and see if we can match anything up. So let's start with the easy ones. So this one, aluminum, is 2.7, and that's exactly what we got for the last one. So that is really encouraging. So I'm going to write AL here because that's the symbol for aluminum. So we've checked off our aluminum. Let's see here. Lead is 11.34, and we've got this one 11.1. That's awfully close. So I think we'll call that one lead. The symbol for that is PB. It's kind of a weird one. Iron is 7.87 and zinc is 7.14. So those might be tough to distinguish because this one is 7.05. That's closer to zinc. So maybe we'll call this one zinc, I'm thinking. You know, let's do that. Symbol for zinc is ZN. And tungsten is 19.3. That one's super heavy. This one's the closest to that. It's still kind of far off, but it's a lot closer than any of the other ones. The next highest is 10. So I think it's safe to say that our cube 3 here is probably tungsten. Tungsten is another weird one with a W as the symbol. And then now all we've got left is copper and iron. Copper is 8.96, which is kind of far off from both of these. And iron is 7.87, which is still pretty far off. So our densities aren't quite right. But as you might know, copper is a reddish metal, so I think it's fairly obvious that this one should be copper. The symbol for copper we have is Cu. And in process of elimination, that leaves iron as our last one as Fe. Now what's really interesting to me is that some of these are off by quite a bit. The aluminum is spot on, which is fantastic. And this one's pretty obvious because it's so lightweight and it's got that nice silvery shine that aluminum should have. So I'm very confident that that one's correct. The lead at 11.1 and 11.34, that's pretty nice too. So I'm fairly certain that this is correct. Another way you could double check yourself is that lead is very, very soft. So you should be able to scratch it with a fingernail, which I did. See that scratch right there? So that's good. So I'm quite confident that these are correct at the bottom here. And then copper, of course, is this reddish metal, so that's definitely what that is. And I know that tungsten is extremely dense, So this one is definitely correct as well. And then we've got zinc is a 7.05 compared to a 7.14. So that's very close. So I think we're good to go on that. And then again, process of elimination leaves us with iron up here. So I'm quite confident that these metals are the correct elements. However, they are off by quite a bit. So why don't we do a little bit extra math and calculate how much we're off by. So the formula that I'm going to use is the percent error. It's the percent error is equal to the accepted value minus the experimental value divided by the accepted value, and then all of that times 100 to give us a percentage. So I'm going to add a column at the end here for our percent error. And then we'll talk about that as we go. So this first one for iron, we have the accepted value for iron is 7.87. And then we'll subtract our experimental value of 9.63 and then divide that by the accepted value again, 7.87, and then everything times 100. So we get a negative 22% error. That's pretty significant. 22% error is not very good. But let's see what the other ones are. And here are the results. So the first two, the iron and the copper, were off pretty significantly by over 20%. So that's not great. But the others were all pretty good. Tungsten, zinc, and lead were all under 5%, which is very good as far as error goes. And then the aluminum, I'm very happy with, is exactly equal to what it should be. But why would we be off at all? Why are our values different from what they're supposed to be? Well, I can think of two possibilities. Well, first of all, our ruler that we used isn't super accurate. You know, I'm limited to just by looking at it, and fractions of a millimeter, we can't really do that with a little ruler. So as I said, calipers would be ideal for this. So that means our volume is probably off by a little bit. And second, some of these cubes might not actually be totally pure elements. Metal alloys are really common, and mixing in even tiny amounts of other metals or substances can change the density of an object quite a bit. For example, this iron might actually be some kind of a steel, which is an alloy with carbon, or stainless steel, which is an alloy with chromium, among other things. So those alloys it'd be reasonable to use those because that would help to stop this cube from rusting. So it's not exactly a pure metal, and that would change the density pretty drastically. A lot of times the tungsten that you buy is also tungsten carbide, which is an alloy with carbon as well, and that's much more common than pure tungsten because it's so much harder. But the fact that our value was extremely close to the pure value suggests that this is indeed pure tungsten. It's very interesting to me that the copper is off by so much because that should be a fairly pure metal. There's not a whole ton of copper alloys besides brass and bronze and things, but those would be very visually different. So this looks like pure copper, but it's off by a decent amount. So I'm not exactly sure what the deal is there. It may be predominantly a volume error, but that's interesting. So I'm curious what the other sets are like because I have several sets that come with this box. And you'll get to measure all of those yourself, and I'm wondering what your error percentages are going to be too. Well, that about wraps it up for these cubes. So hopefully you understand now how to measure density. But you know, while we're talking about density, I thought it would be fun to make a density column. This is actually a really fun and simple experiment that you can try at home. And there's tons of different versions of this, but I'll show you one that I really like a lot.